Imagine a single computer code quietly shaping every major rocket launch for over 50 years. Without it, the Saturn V, the Space Shuttle, and even the Mars Perseverance rover might never have lifted off. That code is NASA Chemical Equilibrium with Applications, or CEA. It's the invisible engine behind propulsion science, calculating how fuels and oxidizers react under extreme heat and pressure, conditions no human could survive. Today, it's used in over 10,000 simulations annually by engineers across the globe. But as rocket technology evolves, so must the tools that power it. In this video, we'll explore how NASA is modernizing CEA to keep pace with new propulsion systems like methane-fueled engines and hybrid rockets. How does a decades-old code stay relevant in the age of AI and high-performance computing? Let's find out. At the heart of propulsion system design lies the principle of chemical equilibrium. This concept explains how chemical reactions reach a state where the forward and reverse processes balance, stabilizing the system. NASA Chemical Equilibrium with Applications, CEA Code, first developed in the 1960s, has long been the go-to tool for modeling these reactions under extreme conditions. A recent report found that CEA is used in over 80% of NASA propulsion analysis projects, from rocket nozzles to combustion chambers. Consider the Space Shuttle main engine. Its performance predictions relied heavily on equilibrium calculations to optimize fuel efficiency and thrust. In these environments, even slight imbalances can lead to catastrophic failures. The CEA program calculates product concentrations from any set of reactants, determining thermodynamic and transport properties with high precision. This makes it indispensable for engineers simulating combustion, shock waves, and detonations. As we'll see, NASA is now modernizing this tool to meet the demands of next-generation aerospace systems. At the heart of propulsion design lies NASA Chemical Equilibrium with Applications, or CEA, a tool that has been instrumental in calculating combustion products and thermodynamic properties. A recent report from NASA Glenn Research Center highlights how CEA provides essential equilibrium chemistry and rocket performance data, used not only across NASA, but throughout the global aerospace industry. Take the development of modern rocket engines. Engineers rely on CEA to model combustion reactions under extreme conditions, ensuring both efficiency and safety. This code calculates chemical equilibrium concentrations from any set of reactants and determines thermodynamic and transport properties for the resulting mixtures. One striking case is its role in optimizing fuel blends for deep space missions, where even minor miscalculations can lead to catastrophic failures. With ongoing updates, such as those outlined in TB 2064, CEA continues to evolve, adapting to new fuels and propulsion technologies. As we look deeper into its modernization, the next scene will explore how these updates are shaping the future of aerospace engineering. The CEA Code traces its origins to the 1960s, a time when NASA was pioneering the science behind high-energy propulsion systems. Initially developed to analyze combustion and chemical reactions under extreme conditions, it became a cornerstone for mission-critical design work. A recent report from NASA Glenn Research Center highlights how the code has evolved to support everything from the Space Shuttle's main engines to the propulsion systems of Mars rovers. For instance, the code was instrumental in calculating the performance of the solid rocket boosters that powered the shuttle into orbit. Researchers say that CEA's ability to model complex chemical equilibria under high pressure and temperature made it indispensable for deep space exploration. Take the Mars Science Laboratory mission. CEA helped engineers predict how the rover's entry, descent, and landing systems would behave in the thin Martian atmosphere. As NASA looks to the Artemis program and beyond, the modernization of this decades-old tool ensures it remains a vital asset. This evolution sets the stage for the next phase of updates we'll explore. TB 2064 marks a pivotal upgrade to NASA Chemical Equilibrium with Applications, or CEA Code. This modernization introduces updated algorithms and a more intuitive user interface, making the tool more accessible for engineers working on next-generation propulsion systems. A recent report from NASA Engineering and Safety Center highlights how these changes significantly expand the code's ability to model complex chemical reactions under high-pressure, high-temperature conditions. For instance, the new version supports calculations for advanced propellants like methane-based fuels, which are central to NASA Artemis missions. Researchers say the updated CEA now runs up to 40% faster than previous versions, improving efficiency in mission-critical simulations. The enhanced code is already being used at the Glenn Research Center to analyze hybrid rocket engines. With its broader capabilities, CEA is evolving from a legacy tool into a dynamic platform for future aerospace innovation. This progress sets the stage for deeper exploration of its real-world applications. CEA plays a pivotal role in calculating rocket performance metrics, including specific impulse, a key indicator of engine efficiency. Engineers rely on these calculations to refine fuel mixtures and nozzle designs for maximum thrust. A recent report from NASA Glenn Research Center highlights how CEA enables precise predictions of combustion products and thermodynamic properties under extreme conditions. Take the RS-25 engine used in NASA Space Launch System. Its performance modeling leverages CEA to ensure optimal operation at high pressures and temperatures. Researchers say CEA's equilibrium chemistry models reduce trial and error in engine development, saving time and resources. The code has been applied in over 200 NASA missions, from the Space Shuttle to Artemis. With modernization efforts, CEA now supports advanced propulsion concepts like hybrid and electrically assisted combustion. As the aerospace industry pushes toward more sustainable and powerful systems, CEA remains an essential tool. This brings us to how it integrates with contemporary design workflows. In hypersonic research, where vehicles travel at speeds exceeding Mach 5, precise modeling of shock waves and detonation becomes critical. NASA Chemical Equilibrium with Applications, CEA Code, plays a vital role in these high-speed scenarios. A recent NASA technical brief, TB264, highlights how CEA supports next-generation aerospace development by calculating chemical equilibrium and thermodynamic properties under extreme conditions. For instance, researchers use CEA to predict how air dissociates and ionizes during shock-wave interactions, enabling more accurate simulations of vehicle performance. Another key application lies in modeling detonation waves in scramjet engines, where precise chemical composition data is essential for optimizing combustion efficiency. With updates to the CEA code, NASA has enhanced its computational speed and expanded its database to include new species relevant to advanced propulsion systems. As hypersonic travel moves closer to reality, tools like CEA remain indispensable in pushing the boundaries of aerospace innovation. This evolution sets the stage for exploring CEA's role in space exploration. Modernizing NASA chemical equilibrium with applications, CEA Code, required a delicate balance. Engineers had to preserve backward compatibility while integrating new features essential for future aerospace missions. A recent report from NASA Glenn Research Center highlighted that CEA has been a foundational tool for propulsion system analysis for decades, used not only within NASA, but across the global aerospace community. The modernization effort, documented in NASA Technical Report TB264, ensured that the updated code could still process legacy datasets while supporting advanced simulations, such as those for next-generation rocket fuels and hypersonic vehicles. Researchers say this balance is crucial for maintaining continuity in missions like Artemis, where historical data must align with new technological demands. The result is a codebase that remains relevant for emerging challenges, from Mars ascent vehicles to sustainable propulsion systems. This evolution sets the stage for the next phase of innovation in chemical equilibrium modeling. At the heart of NASA's CEA modernization effort stands Mark K. Leader, whose work ensures the code keeps pace with evolving aerospace needs. As the lead on this initiative, he highlights that adaptability is key, not just for the software, but for the science it supports. The CEA code, first developed in the 1960s, has long been a cornerstone for propulsion analysis, calculating everything from equilibrium chemistry to rocket performance. A recent report from NASA Engineering and Safety Center underscores how the updated CEA now integrates with modern computing environments, allowing for faster simulations and broader application in next-gen propulsion systems. Consider the Artemis program, where precise modeling of combustion and exhaust is critical for deep space missions. Leader notes that the code's flexibility lets researchers explore unconventional propellants, like green alternatives or in situ resources from the moon. As the aerospace field pushes boundaries, the CEA modernization ensures NASA stays ahead of the curve. Since its inception, NASA Chemical Equilibrium with Applications, CEA Code, has been a cornerstone for propulsion analysis. TB264 now brings this tool into the 21st century with faster calculations and expanded chemical databases. A recent report from NASA Engineering highlights that the modernized version can now process complex combustion scenarios up to 40% faster than previous iterations. Engineers working on next-generation rocket fuels benefit from this speed, enabling more rapid design iterations and performance assessments. The updated code also includes a broader range of chemical species, allowing for more accurate modeling of emerging propellants. One striking case is the inclusion of green propellants like AFM 315E, which are gaining traction in the aerospace industry. Improved output formats make it easier to integrate CEA results into mission-critical systems. As we move into the next segment, we'll explore how these changes impact real-world aerospace projects. CEA's influence extends far beyond NASA walls. Universities like MIT and Caltech integrate it into their propulsion research, while companies such as SpaceX and Blue Origin rely on its calculations for engine design. A recent report from NASA Glenn Research Center highlights that over 1,500 users globally access the tool annually. The CEA code is open source, allowing continuous improvements from the global aerospace community. International space agencies, including ESA and JAXA, use it to model combustion and optimize rocket performance. Researchers at the University of Tokyo applied CEA to analyze green propellants for future missions. This widespread adoption underscores its reliability and adaptability. As new propulsion technologies emerge, CEA remains a vital resource. Its open framework ensures it evolves with the needs of engineers and scientists worldwide. With modernization efforts ongoing, the code is set to support the next generation of aerospace innovations. With the recent modernization efforts, NASA CEA Code now supports more accurate modeling of advanced propulsion systems, including those using green propellants and hybrid fuels. A recent report from NASA Glenn Research Center highlights how these updates enable engineers to simulate combustion processes under extreme conditions with greater precision. Looking ahead, researchers are exploring ways to integrate machine learning algorithms into the CEA framework. This would allow the code to adapt and refine its predictions based on real-world data, improving both speed and accuracy. Imagine a system that not only calculates chemical equilibrium, but also learns from past simulations to optimize future ones. Such enhancements could revolutionize how we design next-generation rockets and spacecraft. As the aerospace industry pushes toward more complex missions, CEA's evolution remains a cornerstone of innovation. This progress sets the stage for the final look at how CEA is reshaping the future of propulsion. As space exploration accelerates, the need for advanced modeling tools becomes more urgent. NASA CEA Code, now in its modernized version, plays a crucial role in analyzing propulsion systems for both current and next-generation spacecraft. A recent report from NASA Glenn Research Center highlights that the updated CEA code now includes expanded thermodynamic databases and improved computational efficiency, allowing engineers to simulate complex combustion processes with greater accuracy. Consider the Artemis missions. These rely heavily on precise predictions of fuel behavior under extreme conditions, something CEA helps model. The modernization effort, documented in NASA Technical Report TB264, reflects a broader push to adapt legacy tools for emerging technologies like green propellants and hybrid rocket engines. With these enhancements, CEA remains a cornerstone in propulsion research, ensuring that as rockets evolve, the science behind them keeps pace. This sets the stage for the final look at how NASA ensures code reliability. The modernization of NASA Chemical Equilibrium with Applications, CEA Code, proves that even legacy tools can evolve with the times. A recent NASA report highlights how the updated CEA now integrates with modern computational workflows, enabling faster and more accurate analysis of propulsion systems. This is no small feat. CEA has been in use for over 50 years, and its continued relevance shows how foundational tools can adapt to new challenges. Consider that the code is used not just within NASA, but across the global aerospace community, from rocket performance modeling to shock wave analysis. the CEA modernization effort, led in part by Mark K., leader at NASA Glenn Research Center, ensures that engineers can continue relying on this tool as they push the boundaries of space exploration. If you're interested in how tools like CEA shape the future of aerospace, be sure to like, subscribe, and check the description for sources and further reading.